How do you decide which deep learning approach fits a task? You need to compare architectures, describe how they work, and evaluate their performance with clear measures. This walkthrough moves from basic perceptrons to transformers, while keeping an eye on strengths, weaknesses, and practical uses. Comparing them helps you judge suitability for specific tasks. The key work involves 3 steps: comparing model types, characterizing their architectural and learning features, and quantitatively evaluating performance, efficiency, and interpretability. Deep learning approaches are diverse and serve many applications. The main model families here are feed-forward neural networks, convolutional neural networks, recurrent neural networks, transformers, and generative models. Each family is tied to certain data types and tasks. Their differences appear in structure, learning behavior, strengths, weaknesses, and the way their performance is measured. Feed-forward neural networks use fully connected layers and are mainly used for tabular data. Their strengths are simplicity and broad applicability. Their weakness is that they struggle with spatial and temporal data, which makes them less suitable when relationships depend on position or sequence. This makes them powerful for visual tasks, but costly when data and models become large. Recurrent neural networks are designed for sequential data such as text and time series. They model temporal dependencies effectively by processing information over time. Their main weakness is vanishing gradients, which makes long-term dependencies difficult to learn and can limit performance on long sequences. Transformers use self-attention mechanisms to handle sequences and show superior performance in natural language processing tasks, such as BERT and GPT. Generative models focus on creating new data samples. They are strong in image synthesis and text generation, but face training instability or model complexity. Important features include layer depth, activation functions, regularization, learning paradigms, and optimization algorithms. Together, these features explain how a model learns, how well it generalizes, and what trade-offs appear during training and deployment. Layer depth determines capacity for hierarchical representations. Deeper networks can capture more complex patterns, but they also risk overfitting. Activation functions such as ReLU, sigmoid, and TON shape nonlinearity and gradient flow, while dropout, L1 and L2 penalties, and batch normalization improve generalization. Supervised learning relies on labeled data for classification and regression. Unsupervised learning explores structure without explicit labels. Semi-supervised and self-supervised learning combine labeled and unlabeled data for better efficiency. For optimization, stochastic gradient descent is widely used, with ADAM, RMsprop, and momentum improving convergence. A single-layer perceptron has one layer of neurons and solves only linearly separable problems, so it suits simple binary classification, such as AND and OR operations. A multi-layer perceptron includes hidden layers, learns hierarchical representations, and solves nonlinear problems through backpropagation and nonlinear activation functions. 0, 2, 0, 3, 0, 4, 0, 5. Nonlinear activation functions let a network learn complex relationships. Without them, the network behaves like a linear model no matter how deep it is. Sigmoid is used in binary classification, but suffers from vanishing gradients. TON improves that somewhat. ReLU is efficient, and leaky ReLU helps with dead neurons. Convolutional layers reduce spatial dimensions while preserving important information. Pooling layers support this process. Max pooling keeps the strongest features, while average pooling retains contextual information but is less effective for edges and textures. From LeNet to ResNet and Inception, CNNs, LeNet was introduced for digit recognition and used alternating convolutional and pooling layers with fully connected layers. AlexNet marked the deep learning revolution with ReLU, dropout, and GPU training. VGG emphasized depth and small filters. ResNet added residual connections. Inception combined multiple kernel sizes for multi-scale feature extraction. CNNs learn spatial hierarchies, gain robustness to small positional shifts through pooling, and scale well to high-dimensional image data. They achieve strong performance in object detection, segmentation, and classification. Their limits include high computational cost, overfitting in large models, limited global context, and task-specific design adjustments. RNNs process data step by step, with each output depending on the current input and previous hidden states. This hidden state acts as memory over time. Training uses backpropagation through time. The core challenge is unstable gradients, which can vanish over long sequences or explode and destabilize learning. LSTM introduces memory cells and gates that control information flow, helping it capture long-term dependencies and reduce vanishing gradients. GRU simplifies this idea by combining some gates, which lowers computational complexity while keeping comparable performance. LSTM suits speech-to-text and text summarization, while GRU fits chatbots and time series forecasting. RNNs are used in speech recognition, where audio waveforms are mapped to text, and in machine translation through encoder-decoder frameworks that are often enhanced with attention. Their strengths include handling variable length sequences and capturing temporal relationships. Their weaknesses include long sequence cost, tuning needs, and dependency limits. Variational autoencoders encode data into a latent space and decode it back, offering stable and probabilistic learning, but often blurry outputs. Generative adversarial networks train a generator against a discriminator, producing sharp images while facing instability and mode collapse. GAN training can suffer from mode collapse, where output variety is limited, and from convergence problems when the generator and discriminator become unbalanced. Diffusion models take a different route by adding noise during training and learning to reverse it. They produce diverse, high-quality outputs and are more robust to mode collapse. Generative models are used for image generation and enhancement, data augmentation, and text synthesis. GANs support art, media, and design with high-resolution images. VAEs and diffusion models are used for super resolution and inpainting. Synthetic data also helps improve performance on small datasets, including medical imaging and rare event simulation. Performance evaluation uses cross-entropy loss for classification, mean-squared error for regression, and tools such as confusion matrices, precision, recall, F1 score, ROC curves, and area under the curve. Case studies include ResNet in image classification, YOLO in real-time detection, and LSTMs in forecasting. Transformers use self-attention and multi-head attention and support BERT, GPT, Vision Transformers, and DAL-E. From perceptrons and CNNs to RNNs, generative models, and transformers, the right choice depends on the task and constraints.